Everyone, good morning. Welcome back to another CMB Bharat seminar. Today we are happy to have Dr. Anto Lonappan from University of California, San Diego as our speaker. So Dr. Anto completed his PhD in 2022 from CISA, Trieste, Italy. Since his PhD days, he is a member and has actively worked on various international CMB collaboration like Polar Simon's Array, Simon's Observatory, LiteBIRD, and CMBS4. He then moved to University of Rome for his first postdoctoral position. In 2024, Anto joined University of California, San Diego, where he continues his exciting work on various aspects of CMB. Today, Anto is here with us to tell us about lensing and delensing strategies for LiteBIRD, the upcoming CMB telescope from space. It's my pleasure to welcome Dr. Anto to this seminar, and over to you.
Thank you very much for the invitation. By the way, can you see my screen?
Yes, we can see.
And you're seeing the presentation screen or the presented screen? I'm a bit doubtful about that.
We can see the slides.
I mean, the full slide, right?
Yes.
Yeah, so, yeah, thank you very much for the invitation. Today I will be talking about the same balancing, issues with that and how to mitigate it in the context of LiteBIRD mission. So the LiteBIRD mission is a worldwide collaboration with various institutions participating. So what is LiteBIRD? It's a space mission. LiteBIRD stands for Light Spacecraft for the Studies of B-mode Polarization and Inflation from Cosmic Microwave Radiation Detection. It is a mission led by JAXA, the Japanese space agency. LiteBIRD is an L2 mission with a frequency coverage between 40 and 400 GHz. It will observe the CMB for 3 years, and the expected launch is around the early 2030s. We are currently undergoing an instrumental rescope, which is expected to complete this year. The main science goal of LiteBIRD is to detect primordial gravitational wave generated during the inflationary phase of our universe, according to the Big Bang cosmological paradigm. Beyond that, LiteBIRD will also be able to explore the primordial non-Gaussianity, the primordial magnetic fields, cosmic bifringens, reionization history, spectral distortion, CMB anomalies, and also the galactic physics. So as I told you in the previous slide, LiteBIRD is a L2 mission. So we are sending the satellite to the Lagrange point, as you can see here, which is like 1.5 million kilometers from Earth to in the opposite direction of Sun. And in the right figure, I mean, I'm showing an animation how we are scanning the CMB from the L2. So that comes to my content of the talk. I start with an introduction to CMB. Then I will discuss the challenges in the detection of the inflationary gravitational waves, also known as primordial gravitational waves. Then I will present the methods and results of the estimation of the lensing deflection of CMB using LiteBIRD CMB maps. Finally, I will discuss how we can mitigate the effect of gravitational lensing, thereby improving the sensitivity to the inflationary phase of our universe. So according to the current Big Bang cosmological paradigm, in the beginning, we had quantum fluctuations. Then came inflation and exponentially accelerated expansion of space. So I'm showing it here. So this phase, the inflationary phase, predicts three important observables. First, a flat universe. Second, primordial fluctuations. We will discuss this in more details in the coming slide. And gravitational waves. I might use the terms primordial gravitational wave and inflationary gravitational wave interchangeably during this talk, but they means the same thing. So after inflation, the universe become hot, dense fireball, or in the cosmologist's language, a photon baryonic fluid. So photons couldn't escape. They were continuously scattering of baryons. Again, in the cosmological terminology, anything beyond an electron is considered as a baryon. So as the universe expanded and cooled, the first atoms formed. So when the electrons and proton combined, making the universe neutral. So this allowed photons to free stream. And these photons are what we now observe as cosmic microwave background radiation, or CMB. So a rough estimate can tell you that in every cubic centimeter just in front of you, there are at least 400 CMB photons. So they are like everywhere. So when this photon left their last scattering surface, so they took a snapshot of that moment. In other words, the anisotropies in the CMB were imprinted by the primordial fluctuations. So this era is called the recombination era. Just before this, the universe was in thermal equilibrium. So the CMB photons followed a Planckian spectra. So the CMB was first discovered accidentally in 1965 by Penzias and Wilson, and later measured by Kobe, WMAP, Planck, and many other balloon and ground-based experiments. So the FIRAS data, which I am showing here, demonstrate an excellent fit to the Planckian spectra. So after the universe became neutral, it enters a period known as dark ages, where we couldn't see anything. So until first generation of stars formed, the light from the stars reionized the universe, making it transparent again. From this point onwards, we can pretty much see the universe. So in this talk, we are going to more focus on the CMB. So let's talk a bit more on the observed CMB. So the leftmost in the case of something similar to the first accidental detection of CMB. So it looks same everywhere. So a bit more cosmological. So CMB is homogeneous, same at every point, and isotropic, same in all directions. So, and the mean temperature in each pixel, so you see here, give a value of 2.7 Kelvin. So if we subtract this mean, the value from all pixels, it looks something like the next mark, showing an anisotropy, not same in direction. And this is equivalent to like 3 millikelvin. And this is due to the fact that our local motion with respect to the CMB frame. From this value, we could estimate the velocity of a local motion. If we remove this value as well from each pixel, then we can see the beautiful CMB map, which has anisotropies at level of 10 microkelvin. So it composed of blue and red spots. So the blue is the hot region and the red is the cold region. So where what we are doing in the pixel space can be done in the Fourier space as well. So this leads to the spherical harmonics. So here we change from the pixel domain go to the spherical harmonic domain. So this is similar to Fourier transform. So Fourier transforms work in the flat space, but the CMB we observe is in the full sky spherical. So from the coefficients of this transformation, so as you can see the A, LM here, we could construct the power spectra similar to the Fourier spectra. And so as you can see, this is the power spectra we define. So this tells us about the variance in the temperature fluctuation. So here the black line represents the best fit line of Planck data. So I given some other dashed lines just to show how different cosmological parameters affect the spectra. So in short, this spectra will tell about the age of our universe, energy and matter budgets, and many more things. The CMB is also polarized. So the local quadrupole anisotropies generates CMB polarization. So the photons coming from hot and cold region separated by like 90 degree can scatter by the electrons, and the resulting photon will be like linearly polarized. So here the full radiation field must be considered when studying the CMB. So we can describe the CMB radiation using the Stokes parameter. So where I represents the intensity, Q and U represents the linear polarization. So V describes circular polarization. So in the panel, you can see the Q corresponds to the vertical and horizontal vectors in a given reference frame, while U is measured at like plus or minus 45 degrees to that frame. So the V parameter measures the helicity of the polarization. However, in CMB studies, we typically neglect the circular polarization, and I will hint at why it's we are considering it as zero in the coming slide. So what is E mode and B mode? So let me show how we are computing the E mode and B modes. So as you can see, the Q and U are measured by orthogonal dictators. However, if we change the reference frame, the Q and U measurements also change. So to handle this, we expand the Q and U in the spherical harmonic domain. So specifically spin-weighted spherical harmonics. So why spin-weighted harmonics? Because temperature is a scalar field or spin 0, whereas polarization is a vector field with spin 2. So this expansion gives us two distinct modes, E mode and B mode polarization. These are named after electric and magnetic field, nothing to do with electric and magnetic field though. So as one is curl-free or gradient-like component, and the other one is like a divergence-free or like curl-like component. So similar to the temperature power spectra, so you can see we could construct the E mode power spectra and also the B mode power spectra. So the key takeaway is that we can construct two observables, E mode and B mode, that are independent of the observing frame. So in the next slide, I will try to explain the physics behind these modes. So that comes to the primordial perturbations, which we hinted in the first slide. So here we are considering two types of primordial perturbations, scalar and tensor. So the scalar perturbation is intrinsically like a sound wave in the photon baryon fluid in the early universe. So thus, they are like compressing and expanding region. As you can see here, I show the E mode polarization which is generated by a scalar type perturbation. So the density of photon baryon fluid is shown in the background gradation. As you can see, the red and blue. So the velocity of the fluid is shown in the yellow arrow. So you can see it's going inside and outside. And the polarization which created by the scalar perturbations is shown in the green lines. So in the right panel, I show the generation of B mode. So the tensor type of perturbation is equivalent to like gravitational wave, which is a transverse wave of distortions in space and time. So gravitational wave has two polarization, the so-called plus polarization and the cross polarization. So here, I show here the cross polarization of gravitational wave is interacting with the last scattering surface with a slant incident angle. So the gravitational wave is propagating towards the black arrow. So as you can see here. So the spatial distortion due to the gravitational wave is shown in the series of ellipses here. So the red or blue arrowheads represents the relative velocity due to the spatial distortion, which causes the blue shift and redshift. So the large scattering surface is shown as a parallelogram here. So, and the gradation represents the phase of the spatial distortion on the space. And the B mode polarization is projected on the surface as shown as yellow lines. So I'm extremely sorry if I made it worse explaining. So in short, the scalar perturbation creates both temperature and E mode anisotropies. But the tensor perturbations creates temperature, E mode, and B mode anisotropies. So what we observe is the total signal. And unfortunately, scalar components dominates. So to get the tensor components from temperature and E modes are like almost impossible. This makes the B mode very peculiar. So we can dictate it as that would be the smoking gun of inflation. So here I want to remind like couple of things. One is the AS, which is the amplitude of the scalar perturbation. And another one is the AT, which is the amplitude of the tensor perturbations. Also, I would like to remind you about the NS, which is the spectral index of the scalar perturbations, which we will see in the coming slides. So in summary, what are the observables? So we observe CMB temperature and polarization power spectra. So in short, we observe CMB in stock parameters, I, Q, and U. Then we convert it to the spherical domain, temperature T, E, and B modes. And then we compute the power spectra as shown here. So we have like temperature, E mode, and B mode spectra here. So the TT power spectra help us to determine the cosmological parameters. The cross spectra of T and E mode, which is TE, and the EE spectra helps further to break the degeneracy in the parameter, allow us to look into the reionization history also. Also, this gives like a good precision on the scalar spectral index, which we saw in the last slide. This all are the indirect evidence of inflation. Especially inflation predicts a near scalar invariant scalar perturbation. Scale invariant scalar perturbation, which gives the spectral index almost equal to 1. So then comes the BB spectra, as shown in the green line in the left figure, which probes directly the energy scale of inflation. So an important parameter here is the tensor-to-scalar ratio, which is the ratio of the scalar and tensor perturbation amplitude, which we already saw in the last slide. And this R, or the tensor-to-scalar ratio, is related to the energy scale of inflation. And here comes the elephant in the room, the topic of this talk, gravitational lensing of CMB. So we're going to talk about it more in the coming slides. So I've shown here the lensing B mode signals as a dotted dashed yellow line. So what is CMB lensing? So while CMB travels towards us, the CMB photons suffers deflections due to the weak gravitational lensing by large-scale structures in the universe. So you can see it as the integrated effect and of a three-dimensional potential wells. So the deflection field, here we are considering it as a Gaussian random field, so which gives us a power spectra as shown in here. So this deflection remaps both the temperature and potential field. So as you can see, the lens temperature and Q and U will be deflected by this deflection field. So next slides discuss the impact of CMB. So what happens to the CMB? So here in the slide, the red line represents the unlensed CMB spectra, and the blue line represents the lensed CMB spectra. So as you can see in the left figure, lensing smooths the peak in the CMB. So for temperature. In the right panel, you can see that lensing B modes, which we already saw it in the last slide. So this lensing B mode, so consider even though there is no primordial signal, so there is no primordial gravitational wave, so we will still find this B mode. And you can see here in the equation, the lensing acts as convolution, both here. But here for the B mode, the lensing B mode, you can see that the E modes are converted to B modes. So what are the current measurements and future? So here I'm showing the current measurements and what LiteBIRD is going to see. So in short, we have measured the TT power spectra, EE power spectra, and the lensing B modes power spectra. So you can see we have been dictated this with few experiments, not few, sorry, a lot of experiments. WMAP, Planck, ACT, BICEP, polar bear. And the LiteBIRD is targeting for the very large angular scales. As you can see, the black dots, black error bars here. So, and we are still searching for the B modes. So if the tensor to scalar ratio is equal to 0.004, as you can see, then the LiteBIRD could dictate it with a good significance. So far, what we know is that our universe is flat and 13.8 billion years old, and our universe is dominated by dark energy, responsible for the late time accelerated expansion. So the second dominating component is dark matter. The observable matter is only just like 4%. So as inflation predicts, the scalar perturbations we observe is near scale invariant. As you can see here, it's like almost 1, not 1. We also have an upper limit to the tensor to scalar ratio by BICEP and Planck collaboration. So in the next slide, so this is my end of this is the end of my introductory slide. So the next slide, I will discuss the another major challenge of the B mode mission, which is foregrounds. So the CMB we observed is not by alone. So the CMB observed is added with other emissions, mostly from our own galaxy. So in the right side figure, I saw the RMS brightness temperature of the signals. As you can see that foregrounds are dominated in all frequency channels. So this is one of the major challenge for the B mode searches. A bit more on the polarized foregrounds. So the foreground map dictated by Planck is shown here in the left side. So here the dust is the thermal emission from the interstellar dust grains heated by the starlights. And here the synchrotron are the emissions from the relativistic electrons spiraling the galactic magnetic field. So in the right side figure, I show the power spectra. So the E mode and B modes are shown in colors. And the dashed line shows the contributions from dust at 150 gigahertz. And the dotted dashed lines shows the synchrotron emission, the power spectra of synchrotron emission. As you can see, both the foregrounds is dominated in the polarization measurements of CMB. So to detect B modes or to detect the inflationary B modes, the first challenge is foreground, which is a frequency dependent component. So by observing the sky in different frequency, we could model it and remove it. Can we remove it completely? Maybe not. So the next challenge is the gravitational lensing, so which converts E mode to B modes, and this is not a frequency dependent signal. So a multi-frequency observation cannot mitigate this thing. So we need to mitigate it some other way, and the procedure is called delensing. Basically means undoing the lensing effects. So we will see this towards the end of the presentation, how we are doing it. So last but not least, the sensitivity of the instrument. So currently, Simon's Observatory started taking data. And CMB-S4 is another proposed experiments, ground-based experiment, which comes towards the end of the Simon's Observatory's time. So from the next slide, I'm going to present our analysis pipeline and result. So LiteBIRD analysis suite. So we start from simulating the unlensed CMB. Then we lens it with a realization of lensing potential using bicubic interpolation. Then we add the dust and synchrotron foregrounds. So this gives us like 15 frequency maps. So then we use these maps to do the classical foreground cleaning technique known as harmonic internal linear combination, or HILC. The foreground clean CMB is filtered appropriately, and we use an EB quadratic estimator to reconstruct the lensing potential. So this lensing potential, with additional traces are co-ordered, and we make an estimate of BMO template, which goes directly to the likelihood to mitigate the impact of lensing B mode and thereby improving the constraints on R. So we have splitted this analysis into two papers. So for more details, you can please check it out. So foreground removal, the harmonic ILC. So how we are dealing with the foregrounds? So the internal linear combination is a classical method which estimates the weights for each frequency maps by minimizing the variance. This is possible because CMB signal is almost constant over the frequency maps. So in harmonic ILC, we obtain the weights in multipoles, thereby allowing us to account for the angular scale variance of foregrounds. So you can see how we are minimizing the variance and thereby estimating the weights, and how we are doing the linear combination with the applying the weights. So here we use two models, S0, D0 and S1, D1. So S stands for synchrotron and D stands for dust. So S0, D0 is a simple model, whereas S1, D1 is a slightly more complex model. So the foreground residual and noise after the foreground removal is shown in the figure in the color. So the green line represents the S1, D1 and the red line represents the S0, D0, a simple model. So as you can see that here in the B mode, in the S1, D1 gives a way high residuals compared to the Lensing B mode. So it's going to be like much higher for the primordial B modes. Yeah, so we use this foreground clean map for the next step, which is the estimation of lensing potential. So we use quadratic estimator. Why it is possible and what is the quadratic estimator? So consider there is no lensing or no other non-Gaussianities. So the covariance of CMB will be diagonal. So which is the power spectra. But if the CMB is lensed, then it generates non-Gaussianity. So this creates off-diagonal elements to the covariance. In other words, CMB lensing induce mode coupling. So this allows us to construct a quadratic estimator with CMB fields. So as you can see here, quadratic estimator CMB fields to use the modes, that is the off-diagonal metrics that are coupled to reconstruct the lensing potential. So we construct such an estimator. This is called Hu-Okamoto estimator. And the normalization of the estimator is given by A here. And the normalization in the ideal case, so represents the noise bias in our estimate, which is called N0 bias. So you can see here. So this is the lowest order noise contributions to the lensing power spectra estimator, even in the absence of lensing. So even though there is no lensing, the quadratic estimator will pick up some spurious correlations between the CMB modes due to random fluctuations. So that's how the N0 appears. So the N0 bias for different pairs is shown here. So for TT, I'm showing it in the blue, and for the EB, it's in the orange one. Also, we could construct a minimum variance method by again by the linear combination. So for our analysis, we chose EB estimator pair, which has the highest signal to noise ratio in the case of LiteBIRD. So here is the power spectra we estimated using our pipeline. So the gray line is the input signal. The black error bars are the one we reconstructed using quadratic estimator. And N0 bias is shown in the red line. So we also show here the N1 bias. So which is the next order correction to the lensing power estimator arising from the non-Gaussianity induced by the lensing itself. So the lensing convergence map comparison. So left shows the input and the right shows the output. So as you can see, the similar structures in the both map. So the impact of foregrounds. So our estimate shows that there is like notable impact by foregrounds. So as you can see in the left panel, the foreground complexity increases the N0 bias. So in the right side, we show the that to make an unbiased estimate of the amplitude of the lensing potential, so we need to model the foreground in a better way. So let's focus on this figure. So here we assume that S1D1 is the correct model. So what we're gonna observe is the S1D1 model. Then we try to estimate the N0 bias, assuming S0D0 and a known foreground case. So in the both case, we can see a clear bias, which is not negligible. So this shows that foreground modeling is important also for the lensing estimate, not only for the B mode searches. So we compare our result with the Planck one. So in the left panel, I'm comparing the N0 bias of Planck and LiteBIRD polarization. So in the terms of signal to noise ratio, which is shown in the right panel, which so the 90 so 90% of the sky can give like a fourfold better signal to noise ratio compared with the Planck polarization. So LiteBIRD's polarization field is just comparable to the Planck temperature field. So we are updating our analysis. You can see the paper will be appearing in this month or next month. How we can improve much more better the signal to noise ratio comparing the Planck. Check the archive. It will appear this month or next month. So that comes to how to mitigate the lensing. So how we are doing the delensing. So it's a very simple process. First, we estimate the B mode, which can be converted from E mode by using the foreground cleaned E mode and deflection field. Then the B mode template is directly subtracted from the B mode data, simple as it is. So if you use the internally reconstructed potential, then it is called internal delensing. Or if you use the external traces like galaxies, cosmic infrared background, or even another CMB experiment like CMB-S4, we call it as an external delensing. So we have considered both this case in our analysis. So the lensing traces. So here I show the survey mass for different traces which we used. So we used the LiteBIRD reconstructed potential and the CIB. We used the CMB-S4 lensing potential. Then galaxy surveys like Euclid and LSST. So this slide shows the correlation coefficient for different traces. So the right side plot shows the individual correlation coefficients of different traces with our input lensing potential. In the left, I show the coefficient when we coord the traces. So you can see that the blue one is the LiteBIRD reconstructed, which is coming from the first analysis. And then to this, we coord the CIB, which give like a better correlation in the scales larger than L equal to 100, then we keep on adding the galaxy surveys and CMBS4 to get the maximum correlation coefficients. And we obtain the highest correlation coefficient by adding all those surveys. And here we show the improvement in the sensitivity of the tensor to scalar ratio. So with multitracer delensing, so we have improved by 20%. So in other ways, so we 20% improvement in the estimate of tensor to scalar ratio compared to no delensing case. Yeah, that's the improvement for the LiteBIRD. And by that, I conclude my slides. Thank you.
Thank you. I think now it's time for questions. Feel free to take the mic and ask.
So why is the weak lensing called weak? Like, what is it compared to?
Yeah, let me share the screen again. Can you see my screen?
Yes.
Yeah. So yeah, so why it's weak? Because the deflection which makes is like extremely small, like at least like 2 arc minutes.
Okay.
Yeah.
Okay, maybe I want to ask two questions, Anto. So first
Yeah.
thing is like, so it's nice to see the improvement in the polarization compared to the Planck temperature. I mean, when we have the 90% sky fraction. So have you considered more complex foreground models, like maybe something better, the maybe high D5, D6, etc. in the case of the Python models instead of.
To show your hand.
Yeah, so we haven't because we were initially checking the first case scenario of whatever the improvement is. But no matter which model we use, like even the complex model, if we can model the foregrounds, then we could the numbers are not going to change much.
Okay.
Yeah, but so as I told in the previous slide, we are going through like a rescope of the instrument itself. So once we done that, we will get to know about the instrument a bit more details. Then we will add the most complex models. So for the current analysis, we are considering D10 and S5. So we are redoing the same analysis with CMB S4. So CMB S4 and LiteBIRD have signed an MOU. For that project, we are considering complex foregrounds. Yeah.
So the second question which I want to ask, maybe it's naive. So I see that when you do the component separation, you are just using HILC. So instead,
Yeah.
what will happen if you use maybe NILC or something? Or is it like you are using harmonic because you are after that you are doing quadratic estimator? So is it like that?
No. So nothing stops us to use NILC. So harmonic ILC was like computationally effective. So if you want to compute the needlet ILC for 22 frequency channels, so the current design of LiteBIRD have like a 22 frequency channels. So so in order to like reduce the computational efficiency and not completely going with like a parametric model. So we decided to go with the harmonic ILC. But again, for the MOU project, CMBS4 and LiteBIRD, we are using needlet ILC.
Interesting. I can see a hand raised from Cosmo MCNS. Can you please? Oh yeah, there's a bunch of group.
Oh, hi, this is Joey. Anto, nice talk. I had a question about the tensor to scalar ratio that you mentioned. So, for LiteBIRD, you showed the constraint is expected to be like 10 is to minus 3.
Mhm.
Was
Yeah,
that the 2 sigma constraint?
yeah, that's right. That's correct. Yeah.
That's the 2 sigma constraint. So, we are expecting like a 2 orders of magnitude improvement, sorry, 1 order of magnitude improvement from Planck.
Yeah, exactly.
Oh, okay. And what about you mentioned the cosmic birefringence measurements, right?
Yeah.
So, how much of an improvement in precision can we expect over the Planck measurements in terms of the EB cross correlation?
Um, yeah, actually, unfortunately, I cannot say the figures, I think, because that's a paper which is just been in the internal review. But yeah, I mean, there is like a good improvement compared to the Planck, much better improvement.
So,
But the paper will be out soon. So the next month, the birefringence analysis paper will be out.
is it also like an order of magnitude improvement or?
Yeah, not exactly, but I mean, better than Planck. Yeah.
Oh, okay, thank you.
Sagnik.
Um, so my question is that in the when we are using the gravitational lensing equation, we are assuming like a point source. Can we also use it for an extended source?
So it's not a point source. You mean a single plane lens?
Yeah.
That might be your question, right?
Yes.
Yeah.
Yes.
So yeah, so we could do that. That's so all the analysis which we have done is in the Born approximation, which considered that it's like we can assume it as a single plane lensing, but the nonlinear corrections can be added. But for the LiteBIRD, maybe it is not possible to reconstruct because LiteBIRD is an instrument with a beam, effective beam of 30 arc minutes. So this will eventually, so if you look at the component separated. Yeah, if you look at the component separated noise, so this is like exploding at L equal to 200, 300. So it will be extremely hard to like reconstruct those small scale lensing potential. So for LiteBIRD, it won't be possible. But other experiments, upcoming experiments can, yeah.
Okay.
I can see one question in the chat. Maybe I can read that for you. So in your primordial power spectrum scalar, you showed some arrows, which I did not understand. Can you explain again? I don't know which one he is referring to, but maybe it's there in the beginning. So Bhuvan Joshi, do you want to take the mic? Oh yeah.
So this arrows,
Maybe the left one.
yeah. So the right, I mean, is he speaking?
No, I don't see him taking the
Yeah.
mic.
So so the left, this arrows represents the velocity of the fluid towards which is going into and going away from the scalar fluctuations. not the polarization. The polarization pattern is shown in the green line.
So there is another question from Pavan. It says, can you explain what is N1 noise term? N0 is clear though. Maybe N0 bias, N1 bias.
Yeah. So the N1 is pretty much coming from the lensing itself. So let me try to think a bit. So N1 basically comes from the non-Gaussianity induced by the lensing itself. I don't know whether it's clear. This is coming from the connected biases, which also coming from the trispectra due to the quadratic estimation.
So
So
maybe
it's, I don't know. Maybe if you want to like a more better explanation, I can
oh,
try
no,
to
I
give
know.
like a more.
I have a follow-up question actually. So
Yeah.
it was that. So is there a way to deal with this N0 bias? Like, so I know that, okay, I mean, the incomplete sky has more N0 bias compared to, let's say, LiteBIRD kind of whole sky survey. So what are the strategies? Maybe this is a methodology question like that we can adopt to deal with. So what I'm asking is like, so we have this, I mean, incomplete sky issues that we deal by using master kind of approach, right? So is there something like that for this N0 bias?
Yeah. So yeah, true. So if you are looking into the Planck 2018 lensing paper, so they have tried something called realization dependent N0. So which basically means, so give me. So as you can see, the quadratic estimator, we use like 2 CMB fields here. So what we can do is we can make a truthful simulation, and we can give, for the one field, we can give the data, actual data, and another field we can give a simulation. So thereby doing this in a couple of ways, we could estimate the N0 bias, which will be realization dependent, which basically means that it is depending on the data. So this is what like Planck have done in 2018 paper. So this help us to reduce the covariance. So can you see my plot here?
Yes, we can see
So
that.
this is the covariance of the lensing potential power spectra. So when we use the N0, just the Monte Carlo N0, you can see that there is correlations in the off-diagonal elements. But when we use the realization dependent N0, unfortunately, I didn't put the equation here. But once we use that, you can see that the off-diagonal correlations which created by the N0 bias can be minimized.
Okay.
Yeah.
Okay. Are there more questions? I don't see any raise hand. Okay. So if not, let's wind up.
Can someone write in the
Pavan
chat?
Pavan is saying that this contains a treatment of N0 bias similar to master algorithm. Okay, thanks for the link, Pavan. We'll check that. Okay, so if there are no more questions, let's thank Anto again. Thanks for wonderful talk. And yeah, so let's wrap the session here. Thank you so much for joining.
Thank you.